All right, I guess we should go ahead and get started. We only have about eight of you in here, but we'll hope for more people to show up. I want to let you guys know I already have practice test four posted. Practice test four, which is practice test for the third online test. It's technically for the fourth test because we had two online tests: online test one, which was also test one; online test two, which was also test two; face-to-face test one, which was test three, and then now we have online test four, which is actually it's online test three, which is test four, and this covers chapters five and six. Last time we actually finished six, so you have until the 19th to get that done. The practice test is up and the test is up. Notice that shifted back 1 week from the original syllabus plan, so just keep that in mind. Your online test will be due Sunday by 11:59 p.m. So make sure you get that done. We are pressing on. I showed you what I think is enough. I mean, there's a lot more material in chapter six, but I usually keep it to the simple stuff like, can you calculate the radius of an orbit around the planet? Can you calculate the altitude of an orbit above the planet? That sort of thing. And that's just a difference of subtracting from the radius, the actual radius of the planet. And there's Lagrange points and all sorts of neat stuff, and I highly recommend you study that. But like I said, I'm just not going to test you on that kind of stuff, so I just want to do the bare necessities. But as I also have been telling you multiple times, you want to make sure anything that has a whole chapter or a whole section of a chapter named after it, like Newton's first law of motion, or Newton's second law of motion, or Newton's law of gravity, or Newton's third law of motion, or Kepler's first law of planetary motion, Kepler's second law of planetary motion, and Kepler's third law of planetary motion. All those are things that at any point now that you've covered them, you should expect them to possibly be a type of question where I'm supposedly thinking I'm giving you a chucker problem by saying state Kepler's three laws of planetary motion. You guys should have these down pat immediately, and you should be prepared to answer them this semester, as well as if you end up taking 242 next semester there as well. And then next semester you'll have, the first law of thermodynamics, the zeroth law of thermodynamics, the second law of thermodynamics, the third law of thermodynamics, all sorts of different stuff. You'll have Kirchhoff's loop rule, Kirchhoff's voltage rule, which is another word for Kirchhoff's loop rule, Kirchhoff's junction rule, which is another word for Kirchhoff's current rule. All of those are things that are big enough that you should commit them to memory, and just never be burned by the fact that an instructor tried to do something nice for you and you didn't think that it was appropriate to memorize something. So that's definitely something you should be doing. Anybody have any questions before we get started? We're going into chapter seven now. All right. So the big deal with chapter seven is that we will be attempting a different scenario to solve problems. So far we've learned about Newton's laws of motion, and they were a vector equation. So Newton's first law of motion really was not necessarily about vectors. It was about when objects do accelerate versus when they don't accelerate. Newton's second law is if they actually have a net external force acting on them, then that's going to cause an acceleration, and that's a vector equation. So that's something you need to know how to do. But now we're moving into a branch of physics where you don't have to use vectors to solve everything. So there's a scalar way you can do a lot of this, and then there's some other work you can do on the backside to get back to that vector stuff that we covered before. I'm sorry, I can't stop yawning. I see that someone asked something to memorize, asked me to repeat that. So yeah, anything that says a law on it, that's pretty much the rule. So when I said Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, Kepler's first law of motion, Kepler's second law of motion, Kepler's third law of motion, that's really for this semester. That's pretty much it. Next semester you'll have, Newton's law of gravity is another one for this semester. But again, next semester you'll have like the zeroth law of thermodynamics, the first law of thermodynamics, the second law of thermodynamics, the third law of thermodynamics, and then Kirchhoff's junction rule and Kirchhoff's loop rule. There'll be more. There'll be Maxwell's equations, stuff like that. But the main thing is right now you need to know those things I told you about this semester, which is Newton's three laws of motion, Newton's law of gravity, and Kepler's three laws of planetary motion. So, as I was saying, you're welcome. The whole purpose of this chapter 7 is, like I said, a new paradigm or a new way to solve problems that doesn't necessarily require vector problems. Excuse me, doesn't require vector analysis is really what I was trying to say. But can't stop thinking that I'm tired and can't stop yawning. So I guess that's going to happen. So I want to remind you that a lot of the terms we use in physics have a parallel in the natural universe. Like we have a phrase called work that we use in the everyday world. Then we have a phrase called work that we use in the physics world, and obviously within a science, you have to have a very specific definitions of such things. Yeah, I'm so sorry. I don't know why. Literally, I haven't yawned at all today until about 2 minutes ago. But anyways, another one's momentum. That's that impulse is another one. Those are all things that have meanings in everyday language, but in physics they have a very specific meaning. And in general, you should think that they do have some bearing on the physics definition that makes it bear resemblance to the non-physics definition. And in this case, we're going to talk about work. So you might think that if you had to mow a lawn, that that would be some kind of work. And if you, for instance, had to push a lot, if you had to mow a lawn with a 50-pound lawnmower that you had to push, and then you had to mow the same lawn with a 100-pound lawnmower that you had to push, you might find in some sense that the work done by the when you push the 100-pound lawnmower was probably twice as much work as you did with the 100-pound, I mean, with a 50-pound lawnmower. That's a good way of thinking about it because it does turn out that work is directly proportional to force. So yeah, that seems reasonable. Another thing you might think about is if you're, let's say, using the same lawnmower in both cases, when you actually are cutting, let's say, a 1 acre lot, you might be using a lawnmower deck that's like 24 inches wide, and you cut a 24-inch wide swath parallel to, let's say, the northern border of the lot, and it's 1 acre. So let's say maybe you go back 120 feet, and then you turn around, make another 24-inch wide swath, and go back the opposite direction parallel to that first one. Well, obviously, if it's an acre, the total area has got to be 43,560 square feet. So you can work out that. But the main thing is if it's 1 acre, we're going to say it's maybe 120 feet back and maybe, some, 100 feet wide or something like that. You have to work out the math, of course. But if it became 2 acres, then you could picture instead of you put walking back 120 feet, you'd have to walk back, let's say 240 feet. Well, it's still going to be just as many strokes wide. So the total distance you travel in the 2 acre case is going to be longer. You could just say and call it work is directly related to area in the case of a lawnmower, but that's not quite as conducive to work being related to distance traveled. So it does turn out that ultimately, if you want to define work in a way that seems consistent with the everyday use of the word work, then that work should directly be related by the force, meaning if you double the necessary force, you're going to double the work. If you triple the necessary work, you're going to triple the force, so on and so forth. And also, if you have to basically go twice as far, then you expect the work to be twice as long, so or twice as high. So in that case, you're thinking work is directly proportional to distance, and work is directly proportional to force. That turns out to be pretty good. I say that directly proportional to. I call that thumbs up behavior. It's the beginnings of science where you're actually studying relationships between two variables. If you remember high school algebra 1, you'd say y is directly related to or directly proportional to x. And then you could make that an equation by saying y equals k, some constant, times x. That is directly proportional to and is a version of thumbs up, thumbs up. But if you had y equals k times x squared, that would be thumbs up as well. If you had y equals k times the square root of x, that'd be thumbs up, thumbs up. If you had y equals k times the cube root of x, that'd be thumbs up as well. And in fact, any power of x would be fine as long as it's a positive power. Fractional powers would be acceptable as long as they're positive. Like I said, y is directly proportional to x to the n power is a thumbs up scenario. If, on the other hand, you found that when the x went up, the y went down, that would be a thumbs up, thumbs down scenario. And we normally write that as y is equal to some constant k divided by x. Again, the more general result would be some k divided by x raised to some n power. As long as that n is not negative, then that's always going to be a thumbs up, thumbs down scenario. So I just wanted you to keep that in mind in terms of what we're thinking about from the grand scale. That also has some bearing on your introduction to, or excuse me, to your labs, specifically linear graphing 1, linear graphing 2, nonlinear graphing 1, nonlinear graphing 2, that sort of thing. That is the precursors of science and the integration of math with science, so that you not only can pontificate about how uh, things behave in the physical world, but you can actually do it with mathematical certainty, so that you can definitively say, "Hey, I make this prediction, and here's the result. And if I expect this much error in my variables, then that error propagates, and that means the result should come up between this number and this number. If it does come up between that number and that number, then you say, oh, well, the experimental results supported my hypothesis. That's a good thing. If it didn't, well, that's a good thing too, because now you have figured out something that's definitely not right about the universe. Specifically, whatever your hypothesis was wrong. So you can go back and find other hypotheses and figure out ways. To be honest with you, probably most of the learning came in the science world from instances where our hypothesis was exactly wrong. So that's why I try to get a positive spin on that for my students, because I don't want you thinking that if you make a hypothesis and it turns out to be wrong, that you're dumb. No, sometimes you have no idea, and just taking a poke at it is a good thing. So now that we have that, let's go on. I will be bringing this up from time to time when we're doing labs and various things. Of course, you have another lab instructor other than me. But the big thing is, I want you to keep in mind that function of y equals k times x to the n power is thumbs up, and y equals k over x to the n is thumbs down. And the simplest case in both cases was with n equal 1. Okay. So, what we now have, I'm going to go ahead and share my screen. What we now have is an idea of, oops, this is not what I meant to do. Sorry about that. What we now have is a relationship that we think will be okay with regards to the definition of work. So, I am going to actually find and express that function of work, and then nail it down a little bit more correctly so I can deal with some of the intricacies that come up in physics problems. So, first off, we have a quantity W called work. So, W is equal to work. And what we're going to say is work is directly proportional to a force. And from the arguments that I just made, it also should be directly proportional to distance. Now, to be honest with you, I didn't really go through the details of working out whether it's distance to the 1 power, distance to the 2 power, distance to the 1/3 power, force to the 1 power, force to the 1/3 power, force to the 2 power, force to the 7 power, whatever. We didn't do all that because we really are free to define it to be anything we want. It's just a matter of what we found is important turns out to be this scenario. Now, another thing that you want to take into account when we're calculating work is that we want a accurate accounting. Like, for instance, if you were trying to push a box to the left, for instance, let's say this is our little box here, and if I wanted to push it to the left, if I applied a force like this to it, then what you would see is I have this component of the force pushing down, which obviously means that's going to make the normal force larger. And what we learned about the normal force tells us that friction is going to be worse when we're pushing down like that. So that's another problem. But in addition to that, we're also going to have a component of force that's parallel to the motion. So when we go to calculate exactly how much work's done, what's more relevant isn't the total force times the total distance, but rather the component of force that's actually parallel to the distance that you travel through. So in order to do that, what we do is we often put the phrase or the term cosine theta or the factor cosine theta in it. And what that does is actually allows us to choose the component of force that's parallel to the displacement vector. So that I'm treating that d as if it's a displacement vector, and it would basically just be ideally if you're walking in a straight line, the work done would be uh, basically force times distance times cosine of the angle between them, where the distance would be basically represented by a distance vector or a displacement vector from where it started to where it ended, and that would be all one straight line so that the vector would lie right on the path. That would be ideal. Okay. But there will be cases where the path does all sorts of crazy stuff like this, and the force might not always have the exact same angle with the displacement vector. So you've got to take into account that. That's where we're ultimately shooting for, is trying to figure out what the work would be in such a serious case. So in this case, what we find out is that we're going to want the work to be either the component of force that's parallel to the displacement, or it's going to be the component of the displacement that's parallel to the force. Either one of those would actually technically be acceptable. However, very rarely do we use the second version where you take the component of D parallel to F, but it could be done in principle. Okay. Now, all of that, of course, also equals d or f times d times cosine theta. But when you have something like that, that theta means an angle. So you need some representation of what we're talking about with regards to theta, d, and f. So this diagram should actually include something along the lines of this, a diagram f, a diagram that shows d, the displacement vector, and when they're tail to tail, that angle would be theta. So that's really the diagram. Now, if you look at that a little closer, let's draw it over here just to make it a little easier for us. So let's say this is the force, and let's say this right here is our displacement vector, and let's say this angle right here is theta. What I would like to point out to you is that we can consider F being made up of two perpendicular components. So this one is obviously perpendicular to the displacement. So this would be F perpendicular to D. And then there's another one that would be F parallel to D. And now that we've made this right triangle, I think you can see that F perpendicular would be F times the sine of theta, whereas F parallel would be F times the cosine of theta. And that's why our force formula has the F and the cosine theta in it. Now, that's not the only way to interpret it. In fact, we could do something like this. Let me borrow this diagram again. Let's do copy. Let's do paste. Okay. So this time I'm going to consider a different right triangle. Let's get rid of all that right there. And what I'm going to do is make it seem reasonable what I just said when I said we could write it as F parallel times D, or we can write it as D parallel times F. That's what I'm trying to show you here. So now what I'm going to do is I am going to take and make a right triangle using D. So notice this is the component of D that would be perpendicular to F. And then this would be the component of D that's parallel to F. And I think you'd see in that case that that's actually D cosine theta, and this F perpendicular to D would be D sine theta. So you can see that's why I was able to write D parallel to F, because that gives me, in this case, the D times the cosine theta. Whereas when I looked at the other drawing, I could say it's F parallel to D because it was F cosine theta that did it. Okay. All of this points to a new mathematical thing called a dot product. So I'm going to introduce that now because it turns out to just be really, really convenient, and it's part of vector analysis that you're learning in 241 and 242. Ultimately, becoming an engineer or a physicist or possibly a chemist or somewhere along those lines, you're going to have to understand vector analysis and vector calculus, and we're slowly building up to that. So far, we've talked about addition and subtraction of vectors, multiplying by scalars, that sort of thing. Now I'm going to introduce you to one of the ways you can multiply two vectors, and that's called a scalar product, but it's also called a dot product. So let me go ahead.
Um,
Yes.
for the first one, why is F parallel equals F cosine, not D parallel equals F cosine?
It could be, but you'd have to think about the green triangle I drew as opposed to the red triangle, because the red triangle is the two components that make up the F, whereas the green triangle are the two components that made up the D. Does that make
I'm
sense?
colorblind. I can't tell which is the red and which is the green.
Okay, well, that would be a problem then, Colin. So what I'm saying here is this guy right here, you can look at this as a vector that when added to this vector, the result is the D vector.
Okay.
Okay. And therefore, D cosine theta is this little part, which is the part of D that is parallel to F.
Okay.
If I did it on this other diagram, then this is the F vector, and it's made of one component pointing this way and another component pointing this way. In that case, this little part is parallel to D, and you can see that it comes from multiplying F times the cosine of theta. Does that make sense?
I think so. I think I'm gonna have to try it out
Yeah,
a couple
it's
times
one of
first.
those things. It's just a matter of which vector are you considering breaking down into perpendicular components. In the diagram on the right, I was breaking down the components of D uh, instead of F, and in the one on the left, I was actually breaking down the components of the force F, parallel and perpendicular to D.
Okay.
So yeah, but it turns out to give you the same formula no matter what. You get a cosine whether you're interpreting it as breaking up the F or breaking up the D. So it
Okay.
shouldn't harm you either way, but that's why I could use it either way. Okay,
All right. Thank you.
you're welcome. All right, so dot product slash scalar product. So it's called a scalar product because you take two vectors and you do some kind of operation on it, and that operation on those two vectors results in a scalar, not a vector. There will be a vector product later, also called a cross product, but right now we're dealing with the a vector product, or excuse me, with a scalar product. And in general, the scalar product is defined to be A dot B. Notice how prominently I write that dot. You want it to really show because it's like multiplication, like you'd use the dot in high school algebra, but it's a little bit bigger deal because it's a multiplication that can only take place between two vectors. So that's why I give it a little bit more significance, just to remind you that hey, I'm not supposed to use this dot between the number two and the number three. I have to use this between a vector A and a vector B, or a vector C and a vector F, or whatever. Now, the definition of it, or a definition of it, would be the magnitude of A times the magnitude of B times the cosine of the angle between them. So, as we did before, you have to include with these formulas an actual diagram. So there's my A vector. And sorry about these vectors not being that straight. There's my B vector, and notice they're tail to tail. So when the vectors are tail to tail, the angle theta has to be the angle connecting the tails to each other, and it's the smaller of the angles because, as you can tell, there's also an angle like this that's a bigger angle. That's not the angle we're talking about. We just want that one when they're tail to tail. Okay, so this is one way to go about calculating this function or this dot product is by taking the magnitude of A times the magnitude of B times the cosine of the angle between them. And another way of writing that is A, B, cosine theta. Now, this turns out to be useful in a lot of different things in a lot of different branches of physics and chemistry and engineering and stuff like that. So you're going to see it over and over again. And one of the things, for instance, in solid state physics, you learn sort of how atoms orient themselves within a lattice, for instance, in solids. And in so doing, you've realized, oh, that often if we imagine a cube in space, then the atoms will be at the corners of the cube. And sometimes you'll have an atom also at the center of the cube. Or sometimes you'll have other atoms at the face of each cube face, like that. And in those scenarios, you sometimes need to understand how much the forces interact with each other, specifically the forces of attraction or repulsion between two adjacent atoms in a lattice like that. And to do that, you actually need to know the angles between the bonds and stuff like that. So a dot product can help you. So we can use this dot product, also called a scalar product. We can use that to find the angle between two vectors, or if we know the two vectors, we can use it to find just the dot product, which we can use to pick off components that are parallel to one another. That's the other big use is we use dot products to find the part of a vector that's parallel to another. So dot products are used to find the part of a vector that is parallel to another, which is exactly what we're looking for in this work scenario. We're actually trying to imagine what component of the force is actually parallel to the motion at each part. Now, now that we have that, I'm going to remind you that we invented these little unit vectors, I hat, for instance, which is also x hat. That has a magnitude. I hat magnitude is equal to 1. J hat magnitude is also equal to 1. And K hat magnitude is also equal to 1. Notice they're 1, not 1 meter, not 1 Newton, not 1 volt, or anything like that. They're just the number 1. That's what I mean by calling them unit vectors. And of course, the same is true. Like I said, this could be X hat, this one could be Y hat, and this one could be Z hat. The same answer either way. It'd still be 1, 1, and 1. Now, we learned a formula in terms of the magnitude of the one vector, the magnitude of the other vector times the cosine of the angle between them. So I'm going to make use of that. Specifically, I'm going to take the vector A, and let's say it is A sub x times I hat plus A sub y times j hat plus A sub z times k hat. Then I'm going to define the vector B as B sub x I hat plus B sub y j hat plus B sub z k hat. And now I'm going to use something that might not seem that reasonable to you. I'm going to just assume that something's true about the dot product because I remembered learning this process in pre-algebra and later in algebra 1 and later in algebra 2. Specifically, if you want to take the dot product of two terms or two expressions like I have here, then the distributive property tells me that I have to use the distributive property to figure out what the product is. So I'm going to assume the distributive property holds, And the reason we're doing that is it turns out there's a bigger concept that's bigger than just your little high school algebra class or your pre-algebra class. There is a concept called an algebra, okay? And there is a concept called a space or a vector space. And if you consider it in that larger scale, then what we're talking about is in an algebra, which is part of some kind of vector space, you have certain rules that must be followed in order for it to meet the criteria of what we call an algebra or a space. Well, those rules that you thought were pretty nonsensical when you were learning them in pre-algebra, like, A times B is equal to B times A, that's a commutative property. Or A times parenthesis B plus C is equal to AB plus AC, that's a distributive property. Uh, Reciprocal properties, all these different properties are things that go into making what we define as an algebra. So it's not weird for me to assume that the distributive property is going to apply when I actually do a dot product. Not only that, a certain linearity is going to apply as well. And what I mean by that is if you have something operate on a linear combination, like some constant A times some vector A, or let's say some vector B, plus some other constant C times some other vector D, if you let one thing operate on it, what the linearity says is that you can just pull those little constants out in front, and then you can let the operator operate on the vector by itself, and then do it again for the other terms so that you'll have different terms. But you'll have basically the constant A times the operation on the vector B plus the constant C times the operation on the vector D. That's the linearity. And what I'm going to tell you is the dot product is a linear operation. The cross product will be, which we're going to cover later too, that's the vector product. That's a linear property as well, or a linear operator as well. So when I go to do a dot product, I'm going to write this as ax I hat plus a y j hat plus a z k hat. In parentheses, there's my prominent dot, bx I hat plus by j hat plus bz k hat, like that. Now, our distributive property tells us that I should take this first term and multiply it by that first term. Then I'm going to take that first term and multiply it by the second term. And then I'm going to take that first term and multiply it by that third term. Then I'm going to do the same thing with the second term in A in the first vector. And then I'm going to do the same thing with the third term in the first vector. Okay. I'm also going to make use of the linearity, and I'll show you how that goes. So let's carry on. What I'm going to do is say AX I hat dotted with BX I hat. So that's just the distributive property. I haven't yet done the linearity thing yet. Plus AX I hat dotted with BY J hat plus AX I hat dotted with BZ K hat plus, now I'm going to go to the second term in the A vector. So that's A Y J hat dotted with B X I hat plus A Y J hat dotted with B Y J hat plus A Y J hat dotted with B Z K hat. Now I got to do the third term. So that's going to be plus A Z K hat dotted with B X I hat plus A Z K hat dotted with B Y J hat plus A Z K hat dotted with B Z K hat. So that's what the distributive property gave me. And it turns out that, yeah, this is exactly right. Now I'm going to show you how to simplify it a little bit more. Uh, I'm going to go ahead and take the fact that this dot product is a linear operation, and what that means is in this first term, notice this first term has an ax, an I hat, a dot, a bx, and an I hat. The linearity means I can pull the scalars out in front, and I'll just have a x b x, and then I'm just left with the dot product I hat dot I hat. Now I can do that with the second term. Notice that's going to be a x b y I hat dot j hat. And I can do it with the third term, which would be a x b z I hat dot k hat plus, and I'll leave that for there right now. I'm going to leave that there and think about these individual terms so we can see a pattern and hopefully save us a little bit of writing. So remember our definition of the dot product was the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them when they're tail to tail. So if I'm making use of that, you can probably figure out what I hat dot I hat is going to be. What's the magnitude of I hat? Anyone? By the way, I did write it on this very page.
One.
Mm-hmm. So we're going to get a 1, and then the magnitude of the other I hat is also 1. What's the angle between I hat and I hat? They're identical. So the angle would be
0.
0 degrees, exactly. Can anybody recall what the cosine of 0 is?
0.
That's the sine. The cosine of 0 is 1. But yeah, that's a typical mistake. It's literally like 70% of the answers I get when I ask that question. But in this case, what we see then is I hat dot I hat is going to be 1 times 1 times 1. So that's just 1. Anybody want to take a guess what I hat dot j hat is going to be?
The
Yeah,
same?
close. It does have I hat has a magnitude of 1. J hat also has a magnitude of 1. But remember, I hat points in the positive x direction and j hat points in the positive y direction. So what's the angle between them if I put those vectors tail to tail?
90.
Very good. And cosine of 90 is
0.
exactly. So what you see, hopefully, the pattern is that whenever you're dot producting two unit vectors that are identical, the answer is just going to be 1. But when you dot product two unit vectors that are perpendicular to each other, the answer is going to be 0. So what we get then is that this whole term is going to be 0. This whole term is going to be 0. This whole term is going to be 0. And this whole term is going to be 0. And this is going to be 0. And this is going to be 0. So all we're really left with, I feel like I left one out. There's got to be a, okay. Now, so all we're left with is the AXBX times 1, the AYBY times 1, and the AZBZ times 1. So we can now say that our vector product is going to be a lot of zeros. Actually, I should probably go back to writing in purple now. There's another 0 there. That's for AYBX. And then I have AYBY. So that one's going to be AYBY. And then I have a 0 for AYBZ. And then I have a 0 for AZBX. And then I have a 0 for AZBY. And then I have a AZBZ for the last one. So We now have another way of writing the dot product. We can say A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them, but it's also AX BX plus AY BY plus AZ BZ. And that's how you can use, for instance, if you have the three components of the two vectors, you can use those to find out an answer for the dot product. You can also use those to calculate the magnitudes of the individual vectors. So you can put that in the AB cosine theta form, and then you can solve for cosine theta, and that'll give you the angle between those two vectors. So that's kind of a nice, helpful sort of thing. Just to convince you of this, let me show you an idea or a way of thinking about this that hopefully will bring it home. So here's a vector, or here's a coordinate system, X and Y. We know about our 3, 4, 5 triangle. So what I'm going to do is imagine that I have this vector right here. That's going to have a magnitude of 3.00 newtons, and it points due east. I'm also going to have another vector that is only 3 units long. Ooh, that other one was supposed to be 4. Sorry about that. I forgot I changed it midstream and forgot to change the magnitude. Oops. So this one should actually be 4.00, not 3.00. And this one's going to be 3.00 newtons. And then, of course, this one is going to be 5.00 newtons. Okay, what I've just done is laid out a 3, 4, 5 triangle. Everybody recognize that? So let's say this is vector A, and let's say this is vector B. Okay, so if that's the case, then A is equal to 4.00 newtons I hat plus 3.00 newtons J hat, and B is going to be 4.00 newtons in the I hat direction, like that. Okay, so let's calculate A dot B. Remember, it's a scalar product, so we should get a scalar out. I'm going to do this because I don't know any angles between them. I have to do this with the components. So I'm going to say 4 I hat. Notice I've simplified to get rid of the units and the sig figs. I'm going to say 4 I hat plus 3 J hat is going to be dotted with 4 I hat. Now that means 4 times 4. Remember, the formula is AX BX plus AY BY plus AZ BZ. So that's what happened when I did first term to first term. Now I'm going to do second term to first term. That one's going to be 3 times 0. And if A actually had a Z component, its component would be 0, and the same thing with B. So that's going to be 0. So I think you all can see that A dot B is in fact going to be 16.0. And obviously this would come out to be Newton squared. So that's what A dot B is. Now, the magnitude of A we know is 5.00 newtons, and the magnitude of B we know is 4.00 newtons. So what we know is A dot B is equal to AB cosine theta, but it's also equal to AX BX plus AY BY plus AZ BZ. Because of that, I can go ahead and fill in what I know. What I know is 5.00 newtons times 4.00 newtons times cosine of theta is equal to 16.0 newtons squared. Notice that just came from the dot product I just calculated up top. Therefore, cosine theta is equal to 16.0 newtons squared divided by 20.0 newtons squared. And 16 divided by 20 is pretty straightforward. You could actually reduce it and get zero point 0.8. And therefore, theta equals the cosine inverse of 0.800. And when you do that, shift cosine inverse zero point 0.8, you get 36.87 degrees, which is exactly what we expect for the 345 triangle. Okay, so that's what I meant by you can use a dot product to find the angle between two vectors. What I did was took two obvious vectors that you knew exactly what the angle should be, assuming you remembered your 345 triangle. By the way, the other one, this angle up here has to be 90 minus 36.87, so it's going to be like 51.13 or something like that. You can do that by taking the dot product of the vector that's 3 newtons with the vector that's 5 newtons, and then you'd get obviously tail to tail would be a little bit differently, but you'd still get basically a estimate of what that angle is, and that would help you. So, anybody have any questions on that dot product stuff? So notice how when I took the dot product, I didn't have any I hats or J hats left. That's important. I keep seeing people every semester learning that it's called a scalar product and learning the formulas, but they'll inevitably have random I hats and J hats all in it. There should be no I hats, J hats, or K hats in any dot product except in the computation part. When the answer's done, it's only a scalar. So you might see units and you'll see numbers, but you're not going to see any unit vectors in there. Anybody have any questions on that? All right, so there's a lot of good and fun ways that you can play with dot products. I'm going to go ahead now and jump to us actually solving a physics problem with it. And then I'm going to simplify or make this a little bit more severe by taking into account how we calculate work if the force actually changes as you move to different parts on the path that you're applying the work. So let's start off with example. Well, actually, before I do that, I should go ahead and mention what the units for work are. So we found that work, and I'm going to put an equal sign with a little dot over it because I want you to know that this is a formula, but it's only a formula that works if the force is a constant and the displacement vector that you're working it with is a constant. Then you get F dot D, which equals F D cosine theta. That's only true if the relative angle between the force F and the displacement vector D doesn't change, and the magnitude of F doesn't change anywhere along the path, and the direction of D doesn't change anywhere along the path. But it is a valid formula in those cases. Now, can anybody guess what the units for work would be? You have F times D here. Anybody tell me what the unit for force is?
Newton.
Yep, 1 Newton. And the unit for distance?
Meter.
Exactly. So when you multiply 1 Newton times 1 meter, you get 1 Newton meter. And we actually define that to be 1 joule. That's Joule. That's named after James Prescott Joule. And if you go to Great Britain, you'll learn there's a beer called Jowls, Joules, and that's actually their family. So that family were sort of industrialists, and they, for instance, bored cannons for the government and would make cannons, and they worked out the heat dissipation and all that sort of thing when they were boring cannons. And they also happened to run a brewery, so they had to work out the heat losses and heat gains from thermodynamics. And ultimately, they were the ones that discovered the mechanical equivalent between heat and work, mechanical energy and heat. And therefore, we named the unit of the joule after them. So it's 1 Newton meter is equal to a joule. The Newton meter can also be a unit for torque, but then we normally leave it as a Newton meter instead of calling it a joule. We never call the unit of torque a joule. Your book does show you, for instance, that the joule is also 10 to the seventh ergs. So 1 joule is equal to 10 to the seventh ergs. So in case you've heard of that phrase, you now know that 10 million ergs is equal to 1 joule. And you also know that 1 joule is actually equal to 0.7376. In this case, it's the unit of the foot pound, which again, that one looks exactly like a unit of torque, and it is, but it's also a unit of energy by the same reasoning that work equals force times distance is a unit of work. Okay, so now let's look at example 7.1.
What
Yes.
the heck is an erg, and is that SI or
The erg is part of the British system, but believe it or not, again, we're the only one that uses the British system anymore. So it's found in things like the R value that your house is insulated with, like when they say R13, that sometimes is expressed in terms of ergs. It's just a unit of energy.
okay?
You can think ergonomic. That's sort of the
Oh, okay.
the origins of it. Yep.
All right.
Weird thing, huh?
Yeah.
All right, so let's look at example 7.1. Again, if you have your book open, this is really helpful, but I'm going to read it anyway. It says a person pulls a 50 kilogram crate 40 meters along a horizontal floor by a constant force FP equals 100 newtons, which acts at an angle 37 degrees as shown in figure 7.3. The floor is rough and exerts a friction force of 50 newtons. Determine A, the work done by each force acting on the crate, and B, the net work done on the crate. Okay, so what we have here is a mass equal to 50.0 kilograms. Notice how I added that zero with the underscore so we can go ahead and get rid of the ambiguity of 50 having an ambiguous number of sig figs. D is going to be 40.0 meters for the same reason. We also have the force by the person is 100.0 newtons. And we have the force due to friction. I'm not going to use his notation. I always use my script F for friction. I'm going to call that 50.0 newtons again for the same reason. And finally, I'm going to say theta is equal to 37 degrees. When you do see that 37 degrees or 51 degrees, you should think 345 triangle. That's sort of what it's for. Okay. Now, let me draw what we're actually looking at here. So, what we have is a box whose mass is 50.0 kilograms. What we have acting on it is a force FP at an angle theta, and it's moving across a horizontal rough surface. Now, when I draw a free body diagram, what that's going to be is this, a 50.0 kilogram mass. Acting on it will be a normal force, Fn. Acting in the negative y direction will be the weight, which is mg. And if you multiply 50 times 9.8, you get 490 newtons. In addition to that, we have this force of 100.0 newtons at 37 degrees. That has a x component given by 100.0 newtons times cosine 37 degrees, which in this case should give us the 80.0 newtons. And this one over here is 100.0 newtons times the sine of 37 degrees. This one turns out to be 60.2 newtons. And I'm underlining the extra non-significant digit there. Now, oops, I should have actually drawn this vector green. Sorry about that, because that's in the positive direction, and this vector should have been green too, because it's in the positive direction. This vector over here, on the other hand, that is the friction vector, and that one's 50.0 newtons, but we do draw that one red. So the main reason that I have to draw this at all is one, I want to show you the advantages of working with work as opposed to Newton's laws, because I don't have to do much with friction, or excuse me, with vectors, but I still have to do some. For instance, right now we don't know what the normal force is, and that is a force acting on it, and we're supposed to calculate what the work done by each of the forces acting on it is. So I have to take the summation of the forces in the y direction equals mass times acceleration in the y direction. And I've explained several times why we're going to treat that acceleration in the y direction to be zero. So in this case, what we're going to get is the normal force minus 490 newtons, and then plus 60.2 newtons. And by the way, the 490 newtons, technically the zero is not a sig fig, so I have to put it that way. But all this is equal to just plain zero because the acceleration is zero. And that means my normal force is going to be 490 newtons minus 60.2. So 490 minus 60.2 gives me 429.8 newtons is my normal force. Okay. Now, we could go ahead and figure out exactly what the acceleration and all that stuff is. It turns out the acceleration is going to be 0.6, and we can use that to calculate how fast it would go at the end of the 40 meters. And when we did that, we'd find out that the velocity is 6.298 meters per second. The whole reason I tell you that is because we ultimately could get that answer another way by using this work stuff going on. But that's what we would get if we worked it the way we did in chapters 3 and 4 and 5. Okay. Now, I want to calculate the work done by each of these forces. So I'm going to say work done by FP is equal to the component of FP that is parallel to D times the D. Well, we see that the D is horizontal, so the component of FP that's parallel to it's the 80 newtons. So that's one way we could do it. I'm going to write 80.0 newtons times D, which is 40.0 meters. And that gives you, of course, 8 times 4 is 32. And that means 3,200 Newton meters, which is a joule. Now, we only had two sig figs, so that means the 3,200 has two non sig figs in there as well. But that's the work done by the force that the person's applying to it. Anybody have any questions on that one? Now, we could have also taken the time to do the dot product. That would be an easy way to do it. Uh, or we could just work out, hey, this force is at 37 degrees. Let's take the component that's parallel to D. Oh, that's the one I already worked out to be 80 newtons. So that's another way of doing it as well. Let's look at the work done by gravity. So the work done by gravity is equal to the force of gravity times the D times the cosine of the angle between them. In this case, I wrote theta because that's the generic angle, but technically we've already called theta 37 degrees, and therefore I should probably put a prime on it or something just to make sure you guys know that I'm not talking about the theta that we have there. It's just a new theta that's the angle between the force of gravity and the displacement vector d. So the force due to gravity is the weight, so that's going to be 490 newtons. The displacement is going to be 40.0 meters. And now we need the angle between them. If we look at our diagram, what we would see is actually what we would see is that the angle between the force of gravity and the displacement is actually 90 degrees. Notice it's this angle right here. So in this case, it's going to be times the cosine of 90 degrees, and therefore we're going to get 0.0 joules is equal to the work done by gravity. Okay. Now we need to calculate the work done by the normal force. So work done by the normal force, which is Fn, is equal to Fn times d times the cosine. In this case, I'll call it theta double prime. But again, the angle between F normal force and d is this 90-degree angle right here. Everybody see that? I keep drawing. So again, we're going to get, in this case, 429.8 newtons times 40.0 meters times cosine of 90 degrees, which gives us 0.0 joules, which equals the work done by the normal force. That's the norm. When your force is acting perpendicular to your displacement, it can't do any work. It's literally, just sort of fighting you, if anything, because it's probably making the normal force larger. And if the normal force is larger, that means the friction is going to be larger. Now all we have is the force due to friction. So I need to calculate the work due to that. Oops. The work due to friction is the friction force times d times cosine of the angle between them. I'll call that theta triple prime. Now notice the vector for the friction force points to the left, and the vector for the displacement points to the right. So what is the angle between the displacement vector and the friction force? Anyone?
180.
180.
Exactly. Good job. So the friction force is going to be 50.0 newtons times 40.0 meters times the cosine of 180 degrees. Do you guys recall exactly what 180 degrees cosine is?
Negative
Negative 1.
one.
Excellent. Good job. So we're going to get basically 4 times 5 is 20. So this is going to be 2,000. But we only have 2 sig figs. So this is 2,000 joules is equal to, and it's negative, by the way, is equal to the work done by friction. So that's the work done by each of the forces. Any questions on that? All right, so that is all part A. like that. Now for part B, what we want is W net. W net would be W due to FP plus W due to gravity plus W due to the normal force plus W due to the friction force. So we're going to get 3,200 joules plus 0 plus negative 2,000 joules, which equals 1,200 joules. So W net is equal to 1,200 joules, which technically we'd have to write as 1.2 times 10 to the 3 joules. That's the way we'd write it without violating our sig fig rules. Now, something very neat that I want you to notice here. If I did the summation of the forces, so this is extra. If I did the summation forces in the x direction equals mass times acceleration in the x direction, what I would get would be obviously 80.0 newtons minus 50.0 newtons, and that's all the forces, is equal to 50.0 kilograms times A. That's the only acceleration we're dealing with, so I don't need to write the A sub x. And therefore, I get 30.0 newtons is equal to 50.0 kilograms times A. So as I told you, A is equal to 0.600 meters per second per second. So there's my acceleration. Now, if I use v squared is equal to v0 squared plus 2ax minus x0, I could find what the final velocity would be. The final velocity would be the square root of, we're assuming it started from rest, so the initial velocity is 0, plus 2 times 0.600 meters per second. Now the x minus x0 is the 40.0 meters. So when I do that calculation, I get the square root, if I can find my square root function, there it is, square root of 2 times 0.6 times 40 gives me 6.928. I might have said that backwards earlier when I was remembering. 6.928 meters per second. And we really only had 2 sig figs there, so that 8 is not a sig fig. So that's the velocity. Now, what I want to show you is the kinetic energy initial. This is something you may or may not have heard of. If you've ever had a physics course, you know kinetic energy. If you haven't, then I'm using the fact that kinetic energy is defined to be 1/2 mass times velocity squared. Since it started at rest, the initial kinetic energy is 0 joules. The final kinetic energy, on the other hand, though, is equal to 1/2 times 50.0 kilograms times 6.928 meters per second squared. And if I square this velocity times 50 times 0.5, I get, lo and behold, 1,200 joules. So that turns out to be not a coincidence. Notice the network was 1,200 joules. Notice the change in kinetic energy, delta K, which is K final minus K initial, is also 1,200 joules. That's not a coincidence. That's called the work energy theorem. And the work energy theorem says that if you calculate the total work done in any process, that total work is always going to be equal to the change in kinetic energy. So that's what we just did is we not only worked and showed you how to work a calculator work problem, but we also showed you that it gave us exactly what we expected based on the work energy theorem, which we're going to cover more in the next chapter. Anybody have any questions on that? All right, let's try another example. This will be example 7.2. And this says work on a backpack. Determine A, the work a hiker must do on a 15.0 kilogram backpack to carry it up a hill of height h equals 10.0 meters, as shown in figure 7.4a. Determine also B, the work done by gravity on the backpack, and C, the net work done on the backpack. For simplicity, assume the motion is smooth and at a constant velocity, i.e., the acceleration is zero. So that's going to happen repeatedly when we're doing these energy related problems is we're trying to sort of thread the needle where we do just enough force to make it move, but not enough force to actually make it accelerate. Because if it accelerates, then the energy is just going to go from work to kinetic energy. And we're trying to work out things like work and potential energy and stuff like that. So a lot of times we'll sort of make that. And what we're doing is we're imagining applying a force that's just big enough to put it in equilibrium. And then we're sort of imagining that a random mosquito or a molecule is going to fly by and hit the object in the bottom just enough to lift it a little bit. And then it'll happen again a little bit later. In other words, we're going really, 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 really slow. Okay, so that it's one way of either picturing it as if we're going really, really slow, or another way is like you're waiting for individual molecules to move it up a little bit. But that's what we're going to do here. This is example 7-2. What we have is M equals 15.0 kilograms. This time it is actually 3 sig figs. H is equal to 10.0 meters. What we want to know is A, the work done by the hiker. So A, we want the work done by the person. That's equal to question mark. B, we want to know the work done by gravity. That's equal to question mark. And C, we want to know the network done. So we want to know W net, which we just talked about. That equals question mark as well. Our diagram, however, is this. We're picturing this as our displacement vector. And in fact, this displacement vector can be thought of as going up an incline. The incline has a height h equal to 10.0 meters, like that. And they're saying this angle right here is theta. And this distance, of course, is d, but they didn't give us that. Okay. So first off, we're going to say work done by the person is equal to F person times d times the cosine of the angle between them, which in general is theta. Therefore, I better put a theta prime there because I've already got theta written on here. What we want to do is realize that the force the person applies is going to be in the upward direction. So here's our little mass. Here's the force by the person. In addition to that, we have a force by weight equals mg, and that is 147 newtons, pointing that way. If we took the summation forces in the y direction equals mass times acceleration in the y direction, with the acceleration being zero, we would find that Fp minus 147 newtons is equal to zero. So Fp is equal to 147 newtons. But you'd also find that this angle is 90 degrees minus theta, and then this angle is 90 degrees. So when I go to calculate the work done by FP, I have to put in the 147 newtons. I have to put in D, which, by the way, we can see from this diagram, cosine theta is equal to adjacent, which is H over D. So D, uh, actually, I should write that a little bit differently or a different place. So D is equal to H over cosine theta. So now I can put that in here and say this is H over cosine theta, where theta is that angle that we have drawn. And then I have to multiply it by cosine of the angle between the FP and the D. So that'd be cosine of 180 because it's 90 minus theta plus 90. So that gives me 180 minus theta degrees. Anybody have any questions on that one? What we're doing there? Okay. Uh, actually, no, my fault. My fault. I was looking at the wrong force here. Sorry. The force, I was calculating it with weight basically. You can see that since this angle right here is 90 minus theta and this angle is 90, then this angle right here has to be theta again. Okay. So sorry about that, making that careless mistake. So I'm just going to multiply this times the cosine of theta. It turns out that in this case, the theta is the same as the theta prime, so it's okay. We can see that the cosine thetas cancel out, and we get that the work done, excuse me, the work done by the person force, WP, is equal to 147 newtons times 10.0 meters, which equals 1,470 joules. Now, when I do the work done by gravity, that's where I'm going to get that 147 newtons times h over cosine theta. And now this time I get the cosine of 180 degrees minus theta. Well, this is a trig identity, but this is the same thing as cosine, negative cosine of theta. So now what you see we're going to get is negative 1,470 newtons. The negative came from the fact that the identity gave us a negative cosine, but once that cosine got there, that cosine canceled out with this cosine, so we just had the negative 1470. So this is the work done by gravity. So I'll circle that off as well. Now we can do, that's part B, and that's part A. Now we can do part C, which says W net is equal to 1,470 newtons plus negative 1,470 newtons, or excuse me, joules. And don't know why I wrote newtons all of a sudden, but I did. So this is actually 0 joules net. And they told us that it wasn't supposed to accelerate. So if he started off at zero velocity, he should stay at zero velocity. That's why the net work done was zero. Anybody have any questions on that?
So he's just standing there. He's not walking anywhere.
He's walking, but he's going so slow that he didn't really speed up. So yeah, he actually moves from the bottom to the top, but in order for you to do the calculation, you sort of have to assume he's going really, really slow.
Okay, because I was thinking like if he was walking any direction, that would add another force, like net force onto there.
Exactly, but that would also that net force would cause an acceleration, and that acceleration would cause a change in velocity. But we're trying to work with a minimal amount of force so that we don't change the velocity at all. Again, it's sort of it's an unrealistic problem in that we're imagining it going so slow, but it's also realistic in that that's what we got to do to separate out what happens when you apply a force just to move it from A to B, as opposed to moving it from A to B and increasing its speed. Does that
So he
make sense?
essentially has a constant velocity, so
Yeah,
that would remove the acceleration.
exactly. So you could imagine him
Okay.
just sort of coasting along at some constant but small velocity. That would be acceptable as well. Or he just went so slow that it took him forever and he ultimately ended up at the top with no apparent velocity.
Okay.
Okay.
Yep.
All right. Well, that's it. Make sure you guys chat me your first and last name if you haven't already. I'm waiting for the last person to leave in case anybody has any questions, but you're all free to go. We will finish up chapter seven next time and go into probably chapter eight.
I have a quick question.
Yes.
Where did you get the cosine 180 minus theta from?
If you look at this diagram, remember the formula for the dot product is the two vectors have to be tail to tail. So when I look over here, I have the weight pointing down and the displacement vector pointing up. So they are tail to tail. So I had to figure out this angle plus this angle.
Okay.
This angle was theta. This angle has to be 90 minus theta. And then this angle is 90. So I added 90 plus 90 minus theta, and that's where I got the 180 minus theta.
Okay, I got it now.
That makes sense? It is a little weird, right?
Yeah.
And I just looked up that trig identity just before class that the cosine of 180 minus theta is negative cosine. That's in the inside cover of your textbook if you had a physical copy of the book.
Well, thank you.
No problem. You're welcome.
Have a good
And
night.
you too. Anybody else have any questions? All right. Well, I guess I will let you guys go. You have a good evening, and remember to get your test done this weekend. When you have a test, you get 3 attempts. Only your highest score counts. It's an online test, and you have to have it done by 11:59 p.m. on Sunday. Make sure you get that done, and your homeworks should be available. I did make, I think, chapter six homework. I think I made that due tomorrow night. So even if you had it due already, I moved the date back a little bit, so you have until tomorrow night to get those. I'm going to do that with both the conceptual and the regular for chapter six. So have a good evening, everybody. Bye.